Today's video is going to focus on two new organic families. These would be alkenes and alkynes. So the difference between alkenes and alkynes are the types of bonds that they have. So alkenes have carbon-carbon double bonds, and alkynes have triple bonds. And when you see these bonds in the molecules, these are what we would call the functional groups. These are the unique identifiers of each of these families. And if we saw an alkene, it would look something like this. So if there was a bunch of carbons in a row like this, if we all had single bonds, this would be a butane. If we notice a double bond, just like that, that is now going to be a butene. So we're going to change the suffix, and we recognize that there's a double bond in this molecule. If we have, and I'm going to move to line diagrams, if we have an alkyne, so something like this, so that if it was all single bonds or all sigma bonds, it would be a pentane. There's 5 carbons there. If you notice that there is a triple bond and it would be identified like this, then you know that this would actually be a pentyne. Okay, so these identifiers, these double bonds and triple bonds, are what we call the functional group of the structure. Alkanes, which we already focused on, their functional group is the fact that they all have single bonds. So let's talk for a couple minutes on the double bond, okay, or the triple bond. In either case, what we know is that when we have organic molecules, such as, I'll use again, ethane as an example, okay? So if I have ethane, the ethane has 2 carbons, and the ane suffix indicates that it has all single bonds. If it has all single bonds, that means it's going to have 1 single bond between carbons. And then we know that the carbons must make up the remaining 3 bonds to hydrogens. So when we change this and we make something with a double bond, so for example, if we have an ethene, okay, so now an ethene will have 2 bonds, a double bond to the neighboring carbon. And how many hydrogens are left over? Well, remember that carbon makes 4 bonds, has 4 valence electrons. So 2 bonds are already used up in that double bond. So that means that the carbon can only form 2 more bonds to hydrogen on either side to maintain that 4 bond structure around each carbon atom. Okay, so every carbon now has 4 bonds. It's just right here, the 2 of the bonds are already used up by bonding to each carbon. So this structure here would be an ethene because the ene suffix represents a double bonded functional group. Now, let's look at these double bonds or triple bonds in a little bit more detail. When we have a double bond like this, one of the bonds is going to be the single sigma bond. And that's what we're showing you right here. This is the little symbol for sigma, the Greek letter. And in this structure, we're showing you, this is ethene, by the way, okay? This is the exact same molecule. You can tell because of the number of hydrogens that are there. And what we're showing you is that the main bond in between the 2 carbons is a single bond. And then this extra double bond that is appearing, or if there was a triple bond, there would be 2 of them. These are what we call pi bonds, okay? So you see the little symbol for pi, and there's the word for it there. And they're showing you that the pi bond is either up here or it's down there. This is not a structure indicating that there are, 3 bonds in total. What this is indicating is that that extra double bond can either be found above or below the single bond. And the reason that it's called a pi bond is because of what the word pi is referring to. We have heard the term pi and we've used it to represent a circle. And this is what is happening when you have double or triple bonds in your organic molecules. Now, I'm going to erase this a little bit just to clean it up a little. So I'm going to erase all that. And what we're trying to show you here is that when you have a double or a triple bond, there is one bond that is the single sigma bond. And then the second bond right here, this double bond that we see, it actually rotates around in a circular fashion, okay? And it circles the sigma bond. So here is your single bond. Here is that double bond, and that double bond rotates around and around. It circles around the sigma bond, and this is why it is called a pi bond. If you had a triple bond, okay, so there's a triple bond between two carbons. One of those carbons would be the sigma bond, maybe the middle one. And then there are two pi bonds that would be rotating and circling the sigma bond. Okay, so that is really important to know. And the reason that that's important is because pi bonds, write this down, pi bonds increase the reactivity of molecules. Sigma bonds, single sigma bonds are fairly stable. Okay, we know that they are stable. That's why most of the fuels that we use and we transport around are alkanes. They have single bonds. They're very safe. They require a lot of energy to react the molecule. But the pi bond, because it's circling around and around and around, other molecules or other reactants can come by and grab those pi electrons. Okay, so those pi bonds are moving around and they're kind of like exposed because they're in this, movement fashion around the single bond. The single bond is actually kind of sheltered because those pi bonds are moving around. And as a result, any kind of molecule that has a pi bond is more reactive because neighboring reactant molecules can take those pi electrons and bond themselves to it. All right, let's go through some examples of where we're going to name some alkenes and alkynes. So let's look at our rule number 1. It says the "ene" suffix is going to be used for an alkene or a cycloalkene. That's our ring structure. And the "-ine" suffix, that's how you pronounce it, "-ine", will indicate an alkene molecule. There are no cycloalkynes. They do not exist. You cannot have a triple bonded molecule in a ring structure. There's too much repulsion with the electrons going on. So number 2 says the longest chain chosen for the root name must include both carbon atoms of the double or triple bond. And then the root chain will be numbered from the end closest to the double or triple bond. So here is an example that I would like you to jot down in your note. So here's an example of an alkene, okay, double bond. And we now know that we would begin to number this molecule from the side closest to the double bond. So I'm going to start numbering from this side. 1, 2 carbons get me to the pi bond. 3, 4, and then 5 right there. So there are no branches on this molecule, but we would number this. The reason that we're numbering this is to indicate the placement of the pi bond. And we always number the pi bond. So the pi is sitting between 2 and 3. We always number with the lower number. It's a 5-carbon molecule, so we're going to call it this, 2-pentene. Because "-ene" indicates that there's a double bond, and now we know that the double bond is sitting on carbon 2. Here is another structure that we'll name. So I'm going to put a triple bond there. You can see 3 bonds, and then I'm going to put a branch in. So we're going to number this molecule from the end closest to the double or triple bond. So if I start counting from the from the left, 1, 2, 3 carbons gets me to a pi bond. From the other side, 1, 2, 3 carbons gets me to the pi bond. So it's an equal distance to the pi bond. When we have a branch, we then go to the branch position and we pick the side that is closest to the first branch, similar to how we named alkanes. So because the right side wins, we're going to start numbering from this side. So 1, 2, 3, 4, 5, and 6. So we number our branches just like we did with alkanes. So on carbon 2, I have a 1-carbon branch. So I have a methyl on carbon 2. It's the only branch. And now I have to indicate the pi bonds and where they are located. You pick the lower number. So the pi bonds are sitting in carbon 3 of the root name, which is 6 and hex. And then this is a triple bond, so don't forget you need a suffix of -ine. So the full name, 2-methyl-3-hexyne. Okay, let's do a couple more. So sometimes with double and triple bonds, you'll see more than one listed. So let's do an example like this. We'll put a branch here, and I'm going to put a pi bond there and a pi bond there. So we're going to number this from the side closest to the pi bond. That pi bonds take precedence over branches. So we're going to start numbering from this side. 1, 2, 3, 4, and then 5. And I have an ethyl group on carbon 3, right? So a 2-carbon branch, and we're going to state the name of that first. And then I have 2 pi bonds. So when I have more than one pi bond, we use a prefix like this, diene or triene. And notice that that comes right before the suffix of the family. So what I need to do is indicate the position number of these pi bonds. So they're sitting on 1 and 3. This is a pentene, but because there are 2 pi bonds, we're going to call it pentadiene. Okay, so you put the di or the tri or the tetra to indicate however many pi bonds you have right before the suffix. Okay, that's how we write it. Now let's look at some cyclic molecules. Okay, so cycloalkenes. So I'm going to give you an example like this one first. Okay, and I'm going to put the pi bond here, and then I'll throw some branches down. Let's put a couple branches there. So what we want to do, we remember without cycloalkanes, we have to number the branches in lowest position order. Okay, so we aren't going to forget about that, but it might not surprise you that the double bond has to be numbered first. Okay, so they get assigned numbers 1 and 2. So we're either going to call it numbers 1 and 2 here, or we're going to reverse it and do 1 and 2. Now, which way we number it depends on the branches. So we want to number the pi bond in a way that the next number, number 3, will be closest to a branch. Okay, so if I keep going this way, I don't get to a branch until carbon 4. So I'm just going to back up. And if I number the other way, 1, 2, now I get to a branch on carbon 3 and on carbon 4. So that is in lower position than going the other way. We're going to have 3 and 4 dimethyl. And then we've got a cyclo, very important that you put that prefix in, pentene. You can say 1 cyclopentene, but you don't have to, because the rule for cycloalkenes is that the pi bond has to be on carbon 1. Okay, so you can put in 1 cyclopentene if you want, but you don't have to. Here's another example that we'll do. So we'll do a 6-carbon ring. I'll throw the pi bond down there. There's a methyl, there's an ethyl. Okay, so let's count. We know this has to be 1, 2. Let's check it out. Carbon 3 gets me to a branch. Let's do it with different colors. We'll do 1, 2, numbering the other way. Carbon 3 gets me to a branch. Okay, so the branches are equally distant, but they're different. They're 2 different branches. So think, what is the rule that we use to break a tie when the branches are different, but they're equally spaced? Remember, we use the alphabetical order rule. Okay, so what we want to do is we want to go with these red ones. Okay, so 1, 2, 3, 4, 5, and 6. And so we have 3 ethyl will be stated first because of alphabetical order, 6 methyl, and then this is a cyclohexene. So in your booklets, you have a few molecules that you have the names for them. And so we want you to try to draw them. And be careful. We often will put intentional errors in the name. And then when you draw it, just go back and look at the structure and make sure that the name that we gave you was correct. And if not, rename it.